Hello and welcome back to Lesson 8 in Module 3, where we are talking about, welcome back, this is the first lesson in Lesson 8, Module 3, about graphing quadratic functions from standard form. Okay, so we talked about vertex form already, and this is standard form, right? Seen it before when we do factoring and things like that. We can also graph from this as well. So we've got a high school baseball player here who throws a ball straight up into the air for his math class. The math class was able to determine that the relationship between the height of the ball and the time since it was thrown could be modeled by the function h of t equals negative 16t squared plus 96t plus 6. So this thing right here represents the height of the ball at any time t that baseball player threw up there. Okay, so time is t in seconds, or t is time in seconds, and then h is the height of the ball in feet. Okay, so what does the domain of the function represent in this context? Well, what variable is like the domain here is our x variable? It's the t's, right? So t, so the domain represents the time that the ball is in the air. Okay, we can be more specific potentially in a little bit here once we do more of the problem to come back and actually maybe do the domain as an interval. Okay, what does the range represent? Okay, naturally we ask about the domain, we'll talk about the range. So the range represents the y values, right, in like a generic sense, but what are our y values here? Well, it's the h's, and what does h represent? Okay, the domain range represents, h represents the height. The height of what, though? The height of the baseball during its flight. Okay, at what height does the ball get thrown? So what height, that means we want to figure out h equals what when the ball gets thrown. So that's like at the very start, right? The start of the flight path of the ball is when it's being thrown. So what time is it at the start? It's t equals what? 0. So we're just going to plug 0 in for t here. Okay, so that's 0, so it goes away, and we just have 6. 6 what? Remember, it's a height, so what would our units be? 6 feet. So there's the initial height. After how many seconds does the ball hit the ground? Okay, so after how many seconds, that means we want to know time equals what, right? How many seconds? Time equals what? Does the ball hit the ground? So hitting the ground, that's a position. What is the height of the ball when it's hitting the ground? H is equal to what? 0. So we're going to set our function here equal to 0. And then how do we proceed? Well, so we could graph this and see where the graph intersects the x-axis. I'm going to go ahead and do this using our tools that we already have with algebra and stuff. So first I see here that there's a GCF I can factor out of -2, which leaves me with an 8t squared minus, not 96, 96 divided by 2 is 48, minus 48t, and then minus a 3. Okay, now if we try and factor this, it doesn't. Even if you try and use AC method here, 8 times -3 is going to be a -24, but there's no two nice numbers that multiply to -24, but add to make a -48. So we can't use factoring. I also would discourage you from using completing the square here, because we need to further factor out an 8, and we'll get a bunch of fractions and stuff. So really, quadratic formula is going to be the way to go, which isn't that much better, right? So anyway, let's do it. T equals, and again, we're just going to use quadratic formula for this. So negative b, so negative 48, plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Okay. So negative 48 is positive 48. Oh, b squared, forgot the b squared there. And then I'm just going to go ahead and just type this whole discriminant in my calculator rather than, trying to do it all mentally here. And we get 2,400 here over 16. Okay, now 2,400 we can divide by 100. Actually, we can divide by 400. Okay, and the square root of 400 we know is 20. Yes, so we can simplify this a little bit better. Nope. There we go. Okay, so 2,400 is the same as root 400 times root 6. Square root of 400 is 20. Which you can then simplify a little bit further here by breaking up the fractions. So 48 over 16, 20 over 16. Okay, like so. 48 over 16 is just 3. That's nice. 20 over 16 doesn't simplify as nicely. We can divide both by 4, though. We get 5 over 4. Okay, now, let's do these as decimals real quick to see if both of these answers make sense in context. We'll do 3 plus 5 root 6 over 4 and 3 minus 5 root 6 over 4. So this is approximately 6.1. Squiggly equals is for approximate. And this is approximately negative 0.06. Do both of these answers make sense in context as times when the ball hits the ground? The answer is no, right? This negative time would not make sense. So we're just going to stick with this one time here of 3 plus 5 root 6 over 4. Okay. Oops. Like so. Okay, which we can say is approximately 6.1. Again, you'll need to talk to your teacher about what they consider to be an appropriate answer here. But I think either one is probably okay in general, because you wouldn't normally say if someone's ball will hit the ground at this time. You'll give them an approximate time in seconds, right? So that's when it'll hit the ground, which then brings us up to the domain here, right? That's when the ball will hit the ground. So what's the smallest time quantity that we can talk about for the domain? Well, the smallest time quantity would be 0, right? It wouldn't make sense to talk about negative time. And what's the farthest time quantity? Well, you might say it's just going to go to infinity, right? Just time goes on for forever. And I guess, like, philosophically speaking, you're right. But the ball's going to hit the ground eventually, and it's going to stop moving. And we know that time now. It's this. And so we're just going to use this time here of the, I'll just use the 6.1 approximation there. Okay. Now we're also asked to find what's the maximum height of the ball that the ball reaches. Okay. And so the maximum height, well, if you think about this again, this is a parabola, right? And the a value is negative, which means it opens downwards. So we're looking at a parabola that looks something like this. So where will the maximum be at what special point? This point right here, aka the vertex. How do you find the vertex in standard form, though? Well, that's a great question. To find the vertex in standard form, the x-coordinate of the vertex will always be located at x equals negative b over 2a, which you may recognize as the front part of the quadratic formula. Okay, negative b over 2a. So let's go back to our function here. Negative b, so it'll be negative 96 over 2 times a, negative 16. So negative 96 over 2 times negative 16, like so. Or negative 96 over negative 32, which will simplify then to 3 exactly. How nice. So that's the time, right? Because again, this is the x-coordinate, or in this case, it's the t-coordinate. So then now that we know the time that the ball is the highest point, how can we figure out what the actual the height is? Well, we know the time, so we'll just plug it back into the function. So it'll be h of 3, which will be negative 16 times 3 squared plus 96 times 3 plus 6. Okay, and we'll just calculate this out. And we get 150. Okay, 150 feet. All right, a few more, goodness gracious. What features of this quadratic function are visible since it is presented in the standard form? So the easiest visible one we can see here was the y-intercept, right? The y-intercept was just this 6, because the 0 in for the t and the 0 in for the t there, cancel those out, left us just with the 6. So that was the most visible thing I would say would be the y-intercept. What features of this quadratic function are visible when it's rewritten in vertex form? Well, obviously it's vertex form, right? So what's visible is the vertex of the graph. Okay, so this leads us to this point, which we will get to in the next video.